Hello everyone. Good afternoon. It's time to start our today's Astroph. Today we have three presenters, Chakri, Vignesh, and Dora. Who is volunteer to go first? Thank you, Chakri.
Okay. Oh, so yes. So today I'm going to discuss about this paper. So this is about the beyond cloud nine, the case of for the discovering for more H1 rich failed halos. So this paper studies this H1 rich starless halos, also called the failed halos. So these are the dark matter halos that contains in neutral hydrogen gas H1, but have not detected the stars. And in this paper, the author mainly focused on this cloud 9, which is a nearby candidate of H1 rich halos, and ask whether these modern cosmological simulations can reproduce these cloud 9 like objects. So in this paper they compare these three simulations, and their main result is that this simulation does not predict the same failed halos population. So this means that the H1 rich halos can become a very useful test for the galaxy formation physics, or especially the gas self shielding environment and the threshold for the star formation. So first of all, what is cloud 9? So the cloud 9 is an H1 cloud near the galaxy M94, and it has a neutral hydrogen gas but no confirmed um stellar component. And this paper notes that the Hubble Space Telescope observation strongly limits the presence of stars in cloud 9, and making it one of the strongest candidates for an H1 rich stellar starless halo. So, mm, so yeah. Is In this paper there are three simulation models. One is the five box NVIDIA LG local group, and the recall eagle. The first one is the firebox, which uses this fire 2 physics. It treats the interstellar medium and the gas shelf shielding more locally and more in detail. And the second one is the NVIDIA LG local group. It is a local group simulation. It predicts the many H1 rich failed halos. And the last simulation is the recall eagle. It uses this calibrated eagle physics and also predict the H1 rich failed halos, but in different mass regions. And also, this paper emphasized that the difference in the gas shelf shielding treatment may be one of the most major reasons why the simulation disagrees. And this is the most important figure in this paper. It compares the neutral hydrogen mass, total gas mass, and the halos mass of the field in these three simulations. And this horizontal line it's denotes the H1 rich threshold boundary between the H1 poor and the H1 rich failed halos. And this cloud 9 also shown in this orange diamond. And the firebox objects are mostly below the near the H1 threshold. mm, H1 threshold. And while this NVIDIA LG predicts that many more halos H1 rich objects. And the last simulation, the recall eagle, which overlaps partly with this five box in H1 mass, but has lower mass uh, in the halo mass. And the main important points are these three simulations. The main points of these three simulations are: the first simulation, the firebox, it shows the very few H1 rich failed halos, whereas the second simulation, NVIDIA LG, it shows that many H1 rich failed halos and the wider mass region. And the last simulation, which is the recall eagle, it is similar to H1 masses to the first simulation firebox, but lower total gas and the halo mass. So in the so the if the astronauts find the many cloud9 like objects, it may support some simulation models more than others. And uh, and uh, this image shows the uh, density and the H1 column density profiles. Mm, uh, and the top panel shows the integrated density profile of the Firebox Cloud9 analog, which is the dark matter gas, and the H1 gas. And the bottom panel compares the uh, uh, projected H1 column density profile of the Firebox and the NVIDIA LG Cloud9 analogs with the Cloud9 observations. And both simulation analogs do not perfectly matches the Cloud9 in the inner region, but this NVIDIA LG agrees better at a larger radius, but not in the center. And the authors suggest that the possible reasons it may be because of the resolution effect in this simulation, or environmental effects such as the RAM pressure stripping, or the Cloud9 may not be completely isolated from this M94. So this is important because the Cloud9's shape and the gas distribution may have affected by its environment, not just by the internal dark matter physics. So uh, the most important results are the these three simulation disagrees with each other because it these three simulations predicts different H1 rich failed halo populations, and this Firebox predicts the fewer H1 rich failed halos, and while this NVIDIA LG predicts many more. And also the author suggests that this Cloud9 alone is not enough. The author wants that it is not enough strongly to constrain the dark matter, the galaxy formation clouds, and this Cloud9 may be affected by its environment near this uh, M94, so more objects are needed. And other results is uh, mm, so the difference between the simulation may come from the how they model the H1 formation and the survival. And this Firebox uses the more detailed shelf shielding treatment, while this NVIDIA LG and the Recall Legal rely more on these analytical prescriptions. And also they suggested that for searching this local universe, to search this region, local universe is the best. They recommended they showed that author says that searching for more failed halos in the local universe rather than focusing on mainly on the high density redshift H1 systems. Mm. So the final conclusion is this paper argues that the Cloud9 like objects are very important because they may reveal the boundaries between the dark halos that forms the galaxies and the dark halos that remain starless. However, a current simulation disagrees strongly, meaning that more observations are needed in future. So the final thing is this Cloud9 may be one of the strongest example for this H1 rich failed halos, but they need many more such objects to understand whether the simulations correctly model this dark matter halos or the gas physics or this galaxy formations. So yes, that is the main conclusion of this paper.
Okay, thank you, Chakri. Is there any question or comments to Chakri?
Chakri, I think this is interesting. I'm interested in how they can identify this starless H1 rich halo observationally. I'm sorry, this is maybe not main focus of this paper. But then, so this system has only H1 cloud, right?
Yes, H1.
H1. So then there's no stars.
Yes.
So then, you observationally, if you want to confirm this, you need to detect H1.
Mhm.
Then also you need to know that there is a dark matter halo. So I wonder, without stars or galaxies, how do they prove it?
So without the stars and the dark matter halos.
Without stars, how they can confirm the dark matter halo? Maybe H1 kinematic. Maybe kinematic mass. I
Mhm.
mean, dynamical mass may be measured from H1 gas motion.
Mm.
Maybe. But anyway, this Cloud9 is kind of confirmed
Yes, this Cloud9 is.
observationally, right?
Yes, yes.
Okay, okay, okay. That's interesting.
Mm.
Okay, thank you, Tetsuya-san and Chakri.
Mm.
If there is no other questions or comments, we can move on to next presenter, uh, Vignesh. Thank you.
Yes, let me share the screen. So I have already posted the paper in both AstroPH sheets and the FP page, so people might have a look at it. So is my screen visible?
Yes.
Okay. Okay. So yes, hello guys. I would like to talk about this paper where they use fast radio burst dispersion measure as an unbiased tracer of matter on large scales. So before going on into the paper, I would like to explain what do you mean by unbiased tracer. So we all know that studying large scale structures is the one good way to understand the creation and the evolution of our universe. However, to study this large scale structure, we need something called as a tracer, which traces the underlying matter density. So which traces how the matter is evolving at different scales. So people often use some sort of tracers like galaxies or weak lensing or CMB measurements, which could be the tracers for tracing how the matter evolves as a function of redshift or some other parameter across different phases in the universe. So however, if people when they use galaxies, this is bit tricky because the galaxies have something called as tracer bias, which means even let's say there is a 10% over density in the matter in a confined volume, that means that this 10 percentage over density in the matter will relate to 20 percentage over densities in galaxy number of galaxies. So basically, if there is more matter, then there will be even more greater number of galaxies. So this bias is not like one to one. If there is 10 percentage of matter, then we can expect 10 percentage of galaxy. It's not that case. It's like a bit more complicated. So usually people use, even though use galaxies as a tracer, it's still we call it as bias tracer. There is some sort of bias, and even at large scales this bias makes a calculation of understanding the large scale structure very complicated process. So for that case, people use two things. One, they use weak lensing and they use CMB. However, these have their pros and cons, which is different from this paper's perspective. But here what the authors claiming is that, here what they are saying is, we can use FRB's dispersion measure as an unbiased tracer, which means that the bias caused by this using FRB's dispersion measure is very limited and very small, in fact negligible compared to the bias caused by galaxies on a large scale. So that is what they are claiming. And we all know that dispersion measure is usually is a direct measure of the number of free electrons along the line of sight. In other words, these free electrons, majority contribution of these free electrons are from diffused ionized gas, which contains almost 90 percentage of this total baryons. And here what they are trying to show here is that if we observe this, if we use this dispersion measure, we could able to observe the large scale structures with a very small bias. That is the main core of this paper. So yes, I'll move on. Okay, so to achieve this, what they are doing is that to achieve this what they are doing is that they wanted to figure out, first important thing is how much bias is caused by FRB's dispersion measure in observing these kind of large scale structures. So for the also, one strong parameter that could potentially bias this calculation is the contribution from the feedback process. So basically, galaxies, like for example black holes or supernova process and every other explosions in the universe, will eject the gas outside of the galaxy, and thereby creating a possibility which could alter the dispersion measure of the FRB. So the authors, what they wanted to figure out is that they wanted to figure out whether these kind of astrophysical events changes the dispersion measure calculation very much. If so, we cannot use this as a good tracer of large scale structure. If the uncertainty level is very small, then we can use it as a good tracer. So that for that they are trying to simulate it. So for this particular case, they are trying to do some particular simulations. So we start for that particular case, they start by considering the fact that total baryons in the field is conserved. That means that there is we cannot create new baryons, or we cannot destroy the baryons. We can push them from one area to another area. And apart from that they divide this entire baryon density field into three contributions. So there are baryons that are stored in diffused ionized gas, and there are baryons that are stored in stars, and there are baryons that are stored in neutral hydrogen. So these three, when they combine these three, we'll get total baryons in the universe. This is a simplistic model, so we can further divide each parameter into sub parameters, but they are keeping it very simple. So what they do is, likewise we can even split this into several sections. And by splitting this particular density function into several other parameters, what they are claiming to see is that they are adding some perturbations, which is given in this equation. And they calculate how this perturbation change the mean density fraction, which is given by this equation. And after looking into everything, this is the important this is the, after looking this into everything, they are trying to simulate the feedback process using flamingo simulations. So this flamingo simulation simulates the supernova feedback, AGN feedback, and different models of feedback, and try to see how the dispersion measure parameter changes. If it changes drastically, then we can say that we can't use FRBs to trace the large scale structures. So this is the important figure that I wanted to show here. So the figure one shows the bias that is caused by the diffused ionized gas, the fraction of the diffused ionized gas, and the combination of the bias and the fraction. So you can see, so if my total bias is closer to unity, which means that we can use FRBs as a good tracer of large scale structures. So you can see that the bias parameter, yes, it varies a little bit, but compared to galaxies and other things, this variation is very small as a function of redshift according to different feedback processes. Also, the evolution of this FD parameter, the fraction of ionized gas parameter, this also changes, fluctuates a little bit. However, these variations are very negligible, like in order of 2% or 3% compared to the simulations. And when we combine these two parameters, this is the bias that is generated by the dispersion measure. you can see that this changes as a function of redshift. However, this changes almost 4 percentage, like very small fraction of this very small fraction of the dispersion measure will change with the help of feedback processes. So what they are, from this what they are trying to claim is that these FRB dispersion measure, it is not biased very largely like galaxies or other stuff, comparing to all feedback processes in the universe. So from this part, they are saying is that no astrophysical events can impact the dispersion measure very much. Yeah, there is some contribution from it, but it's not very strong. So once we figure out that no astrophysical events can change the fraction of the dispersion measure very much, we are pointing out, okay, what can we learn from this particular dispersion measure? So what can we use FRBs to learn the cosmology? How we can use it to learn cosmology? So in cosmology, there is a interesting open question called a sigma 8 tension. So this basically tells that the sigma 8 tension tells us how the matter cluster changes as we move along in different phases of universe. And using cmb, they predict a different value of matter clustering, whereas using late universe tools like weak lensing, they predict that matter cluster happens in a even more different scale than what it was predicted by cmb. So this authors, what they are claiming is that we can use FRB to predict these kind of sigma 8 values, but instead of predicting it in matter spectrum, which is often used in weak lensing, these guys uses angular cross correlation. And this angular cross correlation between the FRB signal dispersion measure and the foreground galaxies, and this cross correlation signal depends on the baryon density instead of matter density and the sigma 8 tension. So using all this, what I wanted to conclude is that FRBs can be used to trace the large scale matter distribution with a very minimal bias, and this bias can be complemented, or this bias can be properly understood if we include other measurements such as 21 centimeter line or other galaxy measurements. And once we do this, we can able to use this particular dispersion cross correlation between galaxy foreground galaxies and the FRBDM signal to constrain the sigma 8 tension. So yeah, that's all I wanted to say.
Okay, thank you, Vignesh. Is there any questions or comments to Vignesh?
Yes.
Vignesh, I have a question.
Yes, professor.
So when they take a cross correlation, how the dispersion measure in host galaxy affect?
Actually, I saw something related to that. I'm not familiar with how that particular parameter affects the cross correlation, because I have no experience in this cross correlation part. But they said that they have some sort of effect here, like several clustering statistics have some effect, and that have been considered, which includes the FRB host galaxies. So I don't know how it affects, because I'm not still familiar with how they take this cross correlation.
Oh, yeah. Because obviously this host galaxy is noise, right, in the
Yeah,
analysis.
yeah, yeah, yeah.
Basically, when they talk about this matter density
Mhm.
or over density, so this intergalactic space, right?
Yes, Professor, it's intergalactic,
So,
it's foreground galaxy.
I see. Oh,
Maybe I have to read that part again, because I'm not familiar with this cross correlation technique. Yes.
oh, I see.
Yes.
Hi, Vignesh. I think extending what Tetsuya-san's question about host galaxies, but host galaxies do contribute to the dispersion measure, right?
Yes.
Um, I, so I'm not sure whether they have compared it with the previous studies for where people have used weak lensing, because Even though the galaxies are bias tracers, but the bias has been well studied. Whereas in the case of FRBs, I know that the localization is a problem and the dispersion measured from the host galaxy is a problem. So I
Mhm.
don't know how reliable these information is. I mean, if they have compared the sigma 8 value or maybe H naught value
Calculated
for
using
these.
this method. So actually, they didn't calculate the sigma 8 per se, but then they have shown a way how to calculate the sigma 8 with the help of FRBs. Um, yeah, one thing they could have done is they could have estimated a sigma 8 value with the help of this tracer and compare it with other,
Hmm.
as you said. But I guess they
Yeah.
haven't do that, I guess. But I need to read the later part of this
Yeah.
paper. They would have given some hints on that.
Yeah, because I know that the people who are working in weak lensing would strongly disagree with this part that even though the galaxies are bias tracers, but the bias has been well studied in previous papers. So I don't know how reliable this estimate or the uncertainties will be on this
Mm,
sigma 8,
I guess the
given for
major
the especially for the observational data. I mean, not for the simulated data, but the observational data.
but then I guess the major form of uncertainty would be, as you suggested, that dispersion measure contribution from host. If the host is well modeled, I guess we can obtain the intergalactic IgM dispersion measure, which
Hmm.
could be useful for the cross correlation. So I guess the
But
major
also
contribution would be the DM
But
host here.
also the positioning, right? The localization of FRBs,
Yeah, it's
their
all like a
redshift.
circular loop. So once you know the location, you
Hmm.
might know the host galaxy, and once you know the
Yeah.
host galaxy, we can study the DM host contribution. So it's all a
Hmm.
circular.
But then
Yeah.
for this cross correlation between galaxy and FRBs, do they really need localization?
We
Uh,
would need the photometric redshifts at least.
yes.
Do
They
they
are saying
need
that
it?
need several parameters, which includes FRB host galaxy and known redshift spec Z.
Specs is required.
Yes.
Or at least photometric redshift in cases where the sample is large. Photometric redshift also plays a part, especially like I know for the galaxy sample, this is what we do. We have the photometric redshifts, and there is an statistically large sample for this photometric data. That's why people use photometric redshifts in case there is no spectroscopic redshift available. But
But then Tomoki-san is using without photometric redshift, right?
Mm.
hmm,
Yes, but I think in order to create figure one,
This one, figure one.
yeah,
This one.
the bias evolution with redshift. Yeah.
bias evolution. In order to make this figure,
Yeah.
we have to know both redshift of
Redshift.
FRBs and
Yes,
galaxies.
yes.
Because
Mm.
okay.
Hmm.
I see.
And only we can model
But
the
then
galaxy's contribution.
wait. Yeah, but then this is they are just checking how bias depends on, right?
Yes, professor.
Then if this is proven, then their final goal is sigma 8, right?
Yes.
For sigma 8 purpose, do they need a spec Z or photo Z for
I guess
FRBs?
they need it. I guess because they are uh, where it is. Yeah, they are saying that they are considering for redshift of the galaxies. So yeah, basically, if the FRB's redshift is known very precisely, then we can contribute what are the galaxies that are foreground to this particular FRB and background to this particular FRB, because that information is crucial for this cross correlation, according to my knowledge, because they only consider the cross correlation between the foreground galaxies and the location of FRB.
Yeah, if
So
you see equation number 7 and 8, I guess it makes more clear about the cross correlation that it requires the
yeah,
galaxy.
it has a dependency on the galaxy's photo Z, or I
Hmm.
mean galaxy's
No,
redshift.
Galaxy is
Redshift.
fine. Well, how
Hmm.
about FRB?
Ah,
FRB redshift.
equation 7 doesn't talk about FRB redshift, but Yeah, it did not exclusively say so, but I don't know. What I understood is that they calculate the foreground galaxies. So maybe if you don't use if there is no strong let's say spec Z of FRBs, if there is no available data for spec Z or photo Z of the FRB host galaxy, then there might be some additional bias caused by this uncertainty in the redshift, because that uncertainty in redshift would introduce more foreground unwanted foreground galaxies or background galaxies into this estimation, right?
Not sure.
Hmm.
Because Tomoki-san is already constraining Hubble constant without
Mm-hmm.
FRB's
Agreed.
redshift, right?
I understand.
Then in equation 7, Hubble constant appears here.
Yes.
Then sigma 8 to 2, right? So then I just wonder if this is very similar to what Tomoki-san is doing or not.
I guess it's kind of similar because they are also using the
Kind
same
of similar.
analogy. Yes,
Yeah, kind of similar, I think. But
they are also using the similar analogy.
In Tomoki-san's analysis, do you assume sigma 8?
eh, I think I assume sigma 8
Hmm.
appears here, but in my calculation, I don't calculate cross correlation between DM and galaxy,
Okay. I
but
see.
FRB and galaxy. So
Hmm.
I'm not sure. In that case, I'm not sure whether sigma 8 appears
Okay.
at here or not.
Okay, this is DM versus galaxy.
Yes,
Yes.
DM field
Tomoki-san
was
is
Galaxy.
FRB position versus galaxy.
Yes.
Okay. I see.
This is the kind of cross correlation between DM field.
DM field as in the
Yes.
galaxy field.
Yes.
I see. Okay.
Okay. Thank you all for discussion.
You
Is
guys.
there okay? If there is no other questions or comments, we can move on to Doro. Thank you, Vignesh.
Okay. Can you see my screen?
Yes.
Okay. Today I'm going to present a paper, and the paper is about random polarization, position, angle behavior across bursts of repeating FRB. So, FRB has highly polarized and have a constant polarization position angle, and they found position angles from repeating FRB. So if FRB show periodic behavior in their polarization position angle, that means can we detect spin or orbital periodicity from position angle across various bursts? So in this paper, they use 4 large polarimetric datasets from 3 FRBs because there's 2 peak in 1 FRB, so there's 4 datasets. So first, they delete data which signal to noise ratio is smaller than 50, and most of the bursts have high linear polarization degrees, so the 4-day rotation can be determined and can be removed. And the continuous position angle curves occasionally orthogonal jumps, but they're extremely low occurrence rates, so they retain these jump features, and they separate position angle to 2 types. One is variable and the other one is flat. It is depends on how much the value of chi square mu. And they try two independent tests. One is non-scalar periodogram. And in They use non-Chicago and also MC and FIP, this one. And the bust and jelly shuffling. In this figure, they have a lot of peaks in different frequency, but all of these peaks are smaller than 3 sigma, so it is not significant. And in figure 3, this figure is from several active days, and the figure 2 is for all data. So we can see in this figure for and FRB, like this one, these two panel and these three are the same FRB, and also these two are the same, and these two. So for the same FRB, peaks is very different. This is the maxima, and so if FRB is from spin, there will be stable frequency. So I don't think FRB is from stable spin. And this figure is the position angle scatter. In the left panel, you can see there's a lot of the large burst to burst position angle variation is very different from 50 to 150, but they are also stable over time because it's kind of appeared. And there are Gaussian-like position angle statistics have stable mean and different width. So I think position angle is stochastic but constrained. And because let me find the figure. And because position angle has no periodical feature but have Gaussian structure, so they use the model dynamic magnetosphere in this model. So that means the magnetic axis is not fixed in this model, and there's stochastic perturbation in this model. So in this figure, the gray dots denotes the projection of the effective magnetic axis, and you can see the magnetic axis wobbling randomly on the sphere. And this figure, the figure 6 shows the position angle distribution for different half opening angles. So when the opening angle is small, it looks like more structured, and if the half opening angles is large, the density of position angle is more like Gaussian. And they do phase bend statistics test again because the lens goggle will miss weak signal. So they guess periods from 1 second to 600 seconds. But they still cannot find the consistent enhancement and coherent modulation. So I think, so in this paper, they didn't find the Lanskagel periodicity, and they also think position angle is the Gaussian population, and also stochastic magnetosphere can explain this both. So I think FRB is not rigid like lighthouse, not from neutron star, and and doesn't have clean rotation beam. So I think FRB is dynamic magnetosphere and stochastic emission geometry. That means the position angle behavior of FRB is not from stable spin. This is the paper.
Okay, thank you, Dora. Is there any questions or comments to Dora?
Dora, I have a quick question. So usually when people try to find a periodicity, I think they try to check the FRB timing first. Say when it arrives, then according to arrival time, then they try to find the periodicity, right? This is the first thing people do. And then I wonder, before going to this polarization periodicity, do they check this standard periodicity for these FRBs?
Oh yes, they mentioned the. Let me find. Here's the different periodicity of different FRB. Is this one?
They all have periodicity?
I think this is the period of different FRB because these are repeating FRB.
Oh, no. This is not saying periodicity, right? So temporal coverage of our data set is spanning approximately. So therefore, this is just a data coverage, how long it is. This doesn't mean it is repeating with this periodicity. Probably there's no periodicity discovered for these samples, maybe.
Oh yes, no.
Therefore,
sorry.
Then using arrival time. Then after that, they also try to find using polarization information. Then
yes,
using polarization, they again didn't detect, I guess.
Yes, you are right.
Yeah, I wonder, say, if this is a case, well, from beginning, we already know that there is no periodicity for these FRBs, right? Then even for such a case, can we really expect the periodicity for polarization? So therefore, I just wonder, there are two FRBs which is confirmed periodicity, right? Say one is, two are active repeaters. I think at least there are two cases which has confirmed periodicity. Then I wonder, why don't they check these two instead of finding new one? Any reason? Because if periodicity is already confirmed, then they may expect periodicity for polarization too, right?
Yes.
Therefore, if they can find it, then that's, I guess that's new, but...
Yeah, but I think that they didn't mention it.
They didn't mention? Oh, maybe it's good to check, I think. If no one checked before, then I think it's worth checking, I think.
Because it's a very new paper. Yes.
Okay.
Thank you.
Interesting.
Okay, thank you so much. If there's no other questions or comments, we can decide on our tomorrow's presenters for tomorrow. Shuri and Terry are already volunteered, and we need one more volunteer for tomorrow. Is there any volunteer for tomorrow Astro PH? Thank you, Tetsuya-san.
Okay, yes.
And also, one other thing is that tomorrow Priyanka and me need to go to Taipei for collect our passport and Polish visas. So I am so sorry, but I cannot set up the Astro PH. So I would really appreciate it if someone can set up the class instead of me. Thank you, Darian. Thank you so much. Okay. And thank you all for your time. See you tomorrow at Astro PH. Goodbye.
Thank you.
Thank you.
Bye-bye.
Thank you.